Accelerator mass spectrometry. Accelerator mass spectrometry (AMS) is a form of mass spectrometry that accelerates ions to extraordinarily high kinetic energies before mass analysis. The special strength of AMS among the mass spectrometric methods is its power to separate a rare isotope from an abundant neighboring mass, abundance sensitivity, e.g. 14C from 12C. The method suppresses molecular isobars completely, and in many cases can separate atomic isobars, e.g. 14 and from 14C also. This makes possible the detection of naturally occurring, long-lived radioisotopes such as 10B 36Cl, 26L, and 14C. Their typical isotopic abundance ranges from 1012 to 1018. AMS can outperform the competing technique of decay counting for all isotopes where the half-life is long enough. Other advantages of AMS include its short measuring time as well as its ability to detect atoms in extremely small samples. The method. Generalizations. The above is just one example. There are other ways in which AMS is achieved, however. They all work based on improving mass selectivity and specificity by creating high kinetic energies before molecule destruction by stripping, followed by single ion counting. History. W. Alvarez and Robert Cornog of the United States first used an accelerator as a mass spectrometer in 1939 when they employed a cyclotron to demonstrate that 3He was stable. From this observation, they immediately and correctly concluded that the other mass-3 isotope, tritium-3H, was radioactive. In 1977, inspired by this early work, Richard A. Muller at the Lawrence Berkeley Laboratory recognized that modern accelerators could accelerate radioactive particles to an energy where the background interferences could be separated using particle identification He published the seminal paper in Science showing how accelerators, cyclotrons, and linear could be used for detection of tritium, radiocarbon 14C, and several other isotopes of scientific interest including 10B. He also reported the first successful radioisotope date experimentally obtained using tritium. His paper was the direct inspiration for other groups using cyclotrons J. Rayspec and FU in France and tandem linear accelerators D. Nelson, R. Courteling, W. Stott at McMaster. K. Purser and colleagues also published the successful detection of radiocarbon using their tandem at Rochester. Soon afterwards, the Berkeley and French teams reported the successful detection of 10B, an isotope widely used in geology. Soon the accelerator technique, since it was more sensitive by a factor of about 1,000, virtually supplanted the older decay counting methods for these and other radioisotopes. Applications. The applications are many. AMS is most often employed to determine the concentration of 14C, e.g., by archaeologists for radiocarbon dating. An accelerator mass spectrometer is required over other forms of mass spectrometry due to their insufficient suppression of molecular isobars to resolve 13CH and 12CH2 from radiocarbon. Because of the long half-life of 14C, decay counting requires significantly larger samples. 10B, 26L, and 36Cl are used for surface exposure dating in geology. 3H, 14C, 36Cl, and 129I are used as hydrological tracers. Accelerator mass spectrometry is widely used in biomedical research. In particular, 41Ca has been used to measure bone resorption in postmenopausal women.